Our next speaker is Matyas Gutai. He's an architect, academic, entrepreneur, and developer of water-filled glass. He's an architecture and engineering background and graduated at Budapest University and the University of Tokyo. Matyas has international architectural experience, worked for offices across the world. He's come to speak to us with research for concept of water-filled glass, and this is something that's been working for over a decade while teaching architecture at the University of Tokyo. So, Matyas, we welcome you.
Hello. Hello, everyone. It's exciting to be here. A lot of innovations. So let's get started. So I wanted to talk to you about water-filled glass. It's a technology I'm working on for quite some time as an academic and now as founder of the startup as well. You may have heard of this technology. It's brand new, and it's patented, but it's been around for quite some time. So we're developing it for since 2007, so quite a long time. How does it work? It's very simple. Basically, it's water in glass, so the name pretty much speaks for itself. Why are we doing this? It's very simple. Water is not a good insulator, but it's an amazingly good absorber. So we can actually control radiation with it, and with it we can move energy very quickly, and this way we can improve the performance significantly. Since we finished about 10 years we spent in R&D, and the product is now ready for market. So we founded a startup, and we are not producers ourselves. We don't want to become producers. We actually offer the technology for glass manufacturers, and they can produce that product on their own. They don't need any technical investment to do it. So if you can do double glass, you can do this. How does it work? How does it save energy? So you probably know this. So typically windows lose energy through convection, conduction, and radiation. Radiation is the big player, 66% on a typical window. You know this. Water is really an amazing absorber. You have seen a lot of these diagrams today. This shouldn't be new. This is basically water. It's the perfect coating. It absorbs energy in the invisible spectrum, and it doesn't absorb at all in the visible spectrum. It's almost zero. It's exactly what we need. So using that, we put this perfect coating in the window. It absorbs energy during the summer before it would get in, and it absorbs radiation during the winter before it would get out. And we're basically circulating that to a heat exchanger, and that gives the energy to any kind of conventional HVAC system, and hence you produce the energy savings. So again, water is not an insulator, but circulating it, you effectively block the heat transfer. So the dynamic U value of the window goes down to 0.35, 0.4, which creates a quite significant savings. It works in hot climates. It works in cold climates. We tested it, obviously, through grants, scientific grants, EU grants, and so on, about a total of 1 million. And using that, we developed the technology so it works in almost all major inhabited climates. You can see on the map the energy savings that it can produce. And this is the bottom line. So about 47 to 72% better than double glass, about 34, 61% better than triple glass. Obviously, we published this. So we published in peer-reviewed publications, so you can read the results in leading journals. They're also amazingly good reading if you can't fall asleep. My wife can testify to that. But they're very serious and dry academic publications, but the bottom line is pretty much there. We obviously validated the models in piloting prototype buildings, so this was one of them. So this was Waterhouse number one, and also Waterhouse number two, so we've reached complexity further. These were small buildings, but since you can stack it up, there is no limit how tall you can go. And we currently started working our first projects, greenhouse projects, residential and industrial mostly, but it pretty much works for any kind of buildings. And again, the way it works is that we're not selling the panel ourselves, so always people contact us, they want water-filled glass, and we work with a local manufacturer. We give them the license, and they produce it for them because we want to cut carbon, and we just want to spread the technology to everybody who wants to use it. It's very easy to work it out. What kind of products are our license partners offering? So obviously there is a new build for new projects. Typically that's a triple layer glass. There's not much, as you can guess, there is a water layer in it. It's from inside. We have a low-E coating typically on the third layer. So that keeps the performance inside. It's very simple and straightforward. Everything is off shelf. The frame is off shelf. The pipes are off shelves. The magic is the spacer between the window, which we teach our manufacturers how to do. So it's very simple. It's a patented solution. But what we are actually really exciting, and most our license partners are really excited about, is the retrofit solution. So again, we are improving radiation, right? So that means because we don't improve insulation directly like other materials, it doesn't really matter for us if the water-filled glass is as a secondary glazing, so we just put it behind an existing facade, or if we put it in a new build, the performance is almost exactly the same. And that's really beautiful because we're not going to cut the built environment to a significant level if we don't address glazing retrofits. And the market is really pushing for us to do that. But glazing retrofits are really painful. They're economically not viable. 30% of the project goes on replacing the window. That's just money out of the window, literally. No pun intended. But in this case, you don't have to do that. You can keep your own facade, and it gives us a price advantage. So this kind of project is actually cheaper for you to do. So it's much easier. The clients doesn't have to move out. You don't have to build a scaffolding around the building. So it's just much easier to work with. And again, this is how it works. So in case you're not familiar with secondary glazing, you literally just put it from the inside. It's very easy. Of course, we are very crazy about carbon. So we did the carbon evaluation. Full life cycle, that's actually one of my fields as an academic. This is the worst case scenario in our carbon case. So obviously, if the panel is a new build, the carbon increase is almost nothing. We have a slight carbon increase because we use typically a thicker glazing, but we put water, which carbon is almost nothing. So there is almost no carbon in case of the new build version. In case of the retrofit version, we are adding an extra window, right? So that's what you see here. That would be typically around 95 kilograms per square meter of the glass, which is completely acceptable. It's completely normal for windows. And the carbon savings on the operational carbon would be around 66 in average for a square meter of water-filled glass, which means that you get your invested carbon back in less than 18 months, which is pretty cool. So it works very well. But again, this is the worst case scenario, right? Because for new build, there's almost nothing. So there are 3 ways for you to save energy with water-filled glass. The base level is just as being a better window with the dynamic U value, which we already published, so I'm not going to talk about it today, but happy to answer questions about that if you have. The second level is that the water can be used as a hot water, for example, for domestic use, which is not included the energy savings that I mentioned before, so in the percentages, but that's the second level, which we already published before. But today, what I want to talk about is something even more visionary, which is basically what we call SEED, which is saving energy through energy distribution between different parts of the facade, which is actually something we're really excited about. And that's the third level of energy savings, which I would like to talk about it today. So what does that mean? So imagine a typical office building. It could be anywhere. You have facade oriented north, south, east, west, which is typically what would normally happen. And the big question that we were asking ourselves, like what happens? We were really curious about it ourselves as well. What happens if there is opposite demands between 2 sides of the facade? And we can move the water very effectively because obviously it costs almost nothing to run a water circulation pump, just to move the water between the 2 facades, and we do nothing else. Are we going to save any energy or not? Does it make sense? So again, obviously, if something would happen, it wouldn't work out in tropical climates or hot climates because you don't have the opposite demand. It wouldn't work in polar climates either. So we had to choose in Köppen-Geiger climate region C or D, temperate or continental. So we tested the theory in 2 cities, London and New York. They are actually very interesting. The reason why we picked them because their temperatures are relatively similar, but their radiation gain is very different. So, for example, New York has strong solar gain also during winter. These are just the data of the climate, but location and so on, which they both Köppen-Geiger see. We used a basic scenario. Our baseline was a double glass unit, U value 1.4, so it's a very typical standard, and we used water-free glass against it. And so obviously we already know that water-free glass outperforms better, but we were curious what happens if we just run between facades. So this is just very quickly the results. So in case of London, north and south, this is the energy performance, the demand on one side, on heating. This is the opposite side, cooling. And what happens is that, and these are the moments of the year when you can actually exchange energy. So this is in case of double glass, in case you would be able to do that, but obviously we don't have really a technology to do that, so it was just a theoretical. This is in case of water-free glass, the same results. And you can actually move quite a lot of energy over the year and save quite nice amount of energy. You will see the numbers at the end in my final slide. This is east and west. So it's much less, obviously, because of the type of the solar gain. It's quite low, actually, the energy saving potential. But it should be noted that we ran the simulation between office hours, so between 9 o'clock and 5 o'clock. So obviously that limited the energy, the daylight impact quite significantly. But again, water-free glass is better. But it's not really exciting. You'll see east and west doesn't work really well unless you do the simulation for the whole day. New York was actually much more promising because, again, as I said, the daylight has a much bigger impact. So actually, you do have significant differences, especially during winter. So basically, as you can see, the potential for energy exchange is actually really high. And here you can see it for water-free glazing, which was quite high as well. So it's actually quite interesting because normally if you have overheating in the winter, you would open the window and do some natural ventilation and get done with the job. And yes, that's a reasonable thing to do. But actually you could pass, if we could pass that heat to the opposite side, you could make significant different savings. East and west is again less exciting for New York, again simply because mainly we run the simulation between 9 and 5, and that impacts the model quite a lot. Because obviously in the winter it's when most exciting things can happen in terms of energy exchange, and then obviously in the spring and the days are longer. So in that case, obviously the results are not less significant, but they are still quite interesting. So these are the numbers. So this is that we already knew before we wrote this paper, because these are from our previous papers. So these are the energy savings potentials. Using the basic levels of the energy savings with water-free glass. Again, depending on the city, but they are quite similar. New York is actually one of the best places for water-free glazing, again, because of the daylight potential. And these are the additional savings that you can do if you literally do nothing. Just put two windows on opposite sides and run water between them. No heating, no cooling. You can actually, from the north and south, you can actually save up to 12% just by doing that, which is pretty exciting because that's really simple to build and it's really simple to maintain. There are just some few key points. So obviously, the results were that it grants further investigation, which we are actually doing right now. And we also calculated the coefficient of performance of such kind of system. Again, we're just running a water circulation pump, right? So it's quite high. It's about between 19 and 25, which is ridiculously high, actually. But it's the case because water circulation pumps have almost no energy consumption. And 7.3 and 13 between east and west. But again, as I mentioned, the simulation only considered office hours. And if there is an extended simulations, there would be higher savings probably between east and west. This was also a lesson for us to learn. So obviously that's something we are going to do more in the future. Yeah, I'm almost on time. So thank you very much for your attention. Again, we are always excited to talk to anyone who's interested. If there are any questions, please let us know. I'm most active on LinkedIn. So if you just look up my name, please feel free to connect with me. I'm more than happy to talk to your questions. I'll be around for the remaining days as well. And if you would like to write an email, if that's your way, absolutely, you're welcome to do, and happy to help you out. Thank you very much for your attention.